Okay, so this is going to be section 2.3, day 2. It's actually a continuation of what we did last time, except this time we're going to talk about a couple of more formulas that you guys are going to use, as well as what's called higher order derivatives. So we're going to be able to apply the differentiation formulas to functions and be able to look at some applications of the higher order derivatives. In order to do this, this is something that we'll actually prove later, but for now I just need to kind of let you know the derivative of sine of x is cosine of x. And the derivative of cosine of x is the negative sine of x. For right now, just accept that those are true. I will be showing you how to actually prove all of this in the next section. But in order to be able to do some of the problems that we have here, we need to know that. All right, so just refer to those as we go. So the product rule, which is a rule for two functions that are being multiplied together, says if you have f and g and they are differentiable, again, just meaning you can take a derivative, then the derivative of f times g of x is going to be the derivative of f of x times g of x plus the derivative of g of x times f of x. So to kind of write this in, I would guess you would say more layman's terms, if we call this our first function and we call this one our second function of the two that are being multiplied, you might want to think of this as the derivative of the first function times the second function plus the derivative of the second function times the first function. Sometimes that helps just to think of it in those terms. But it is technically the derivative of f times g plus the derivative of g times f. Now, because this symbol in the middle is a plus, the order doesn't really matter. Technically, I could have done the derivative of g times f first and then multiplied that, excuse me, then added that to the derivative of f times g. I can do it in either order with the product because it's an addition, so order doesn't matter. The reason I do it like this is going to become apparent when we get to some of the next rules. So let's go ahead and see if we can actually apply this rule. So we want to calculate the derivative of each function. So you should be able to clearly see in h that h is a product of two different functions. You've got 3x minus 2x cubed and 5 plus 4x. According to our product rule, it says that if I want to take the derivative of h, we're going to take the derivative of the first function. The derivative of the first function is going to be 3 minus 6x squared. And then multiply that by the second function. Don't do anything to it. Just multiply it by the second function. And then add. Now I take the derivative of the second function, which is just going to be 4. And then I multiply that by the original first function. All right, now I'm going to actually go ahead and I'm going to FOIL all this stuff out and simplify it because I want to kind of prove a point and show you something here. So if we FOIL out this first thing, we're going to get 15, let's see, what is that? Minus 30x squared plus 12x, it's the inside and outside there, and then minus 24x cubed. And then I'm going to go ahead and distribute the 4 into the second parentheses, so we get a plus 12x minus 8x cubed. And then I'm going to go ahead and just combine all my like terms. So let's see, I've got a negative 24x cubed and a negative 8x cubed, which is going to be negative 32x cubed. It looks like I only have one squared term, so that's minus 30x squared My x terms, I've got 12x and 12x, so that's plus 24x. And one constant term, which is 15. So that's the most simplified version of our derivative. Did I have to do all that? No, not necessarily. There might be reasons in the future that we want to simplify these things, but just to take the derivative, this first line right here would have been acceptable. But what I want to show you is I had two polynomials being multiplied together. I very easily could have just gone ahead and FOILed these things out. So let's go ahead and do that. So that's going to give us 15x. Outside is going to be 12x squared. Inside is going to be minus 10x cubed. And then the last is going to be minus 8x squared. If I rearrange that stuff, I'm going to get minus 10x cubed. I did something wrong. Oh, 8x to the fourth. What am I thinking about? Let's try that again. So the 8x to the fourth is going to be first. Minus 8x to the fourth minus 10x cubed plus 12x squared plus 15x. So that's really h of x. Now, if I wanted to go ahead and take the derivative of this, just using the power rule, well, let's see. Negative 32x to the third. Good. Minus 30x squared. Good. 24x. Good. And 15. So the derivative of this right here is what we actually got by doing the product rule. In this case, it probably actually would have been easier just to go ahead and FOIL the first two and then just take a straight power rule derivative. Just wanted to show you that the power rule still works. It applies and it still actually works. Power rule is not really meant for something that you can actually simplify first like I just did. It's actually meant for things like what you have below. So in the second one, we have that f of x equals x times sine of x. Once again, that is clearly two different functions. X and sine of x are being multiplied together. This you cannot algebraically simplify anymore. There's nothing to FOIL together. There's nothing to do there. So we have to use the product rule in order to find this derivative. And this is also why I gave you the derivatives of sine and cosine, because we'll use these in the next two problems. So if I want to take the derivative of f according to our product rule, it is the derivative of the first function. The derivative of x is 1 times the second function plus the derivative of the second function, which is cosine of x, times the first function, which is x. The only thing you can do, because that is the derivative, the only thing you can do now is kind of clean it up. Don't really need to have the 1 out in front of sine of x. And typically, for multiplying a polynomial times a trig function, we're going to put it in the front. So that'll just become x cosine of x. And that is your derivative of f of x. All right, let's do one more. The derivative of g of x will be g prime of x. Now we have two different things that we have to think about here. First of all, this first one is the product of two things. The second one is just a subtraction, and it's technically not a product that we have to worry about. So let's deal with the first part. Let's deal with the 2x cosine of x. So if I take the derivative of 2x, that's 2, times the second function, cosine of x, plus the derivative of cosine, well, that's negative sine of x, times the first function, 2x. Okay, that's just doing the product of 2x cosine x. Now I still have to worry about this minus 2 sine of x. Well, remember that in this case, minus 2 is just a constant. And remember, you can pull a constant out in front before you do the derivative. So I can just do minus 2 times the derivative of sine of x, which is cosine of x. Now we can just simplify this thing. What we have, by the way, is still the derivative, but it's better to clean it up if you can. Well, let's see. I've got a 2 cosine of x, excuse me, and a minus 2 cosine of x. These two things are going to go away. Wonderful. Then I can pull the negative 2x, the positive 2x out in front, and we'll have negative 2x sine of x. Really, that's like having a negative 1 out in front of the sine of x, so it's like negative 1 times 2x, so it's negative 2x sine of x. So that's it. That is our derivative using the product rule. The product rule can be extended to more than one set of products. For example, we could have a derivative where we have a product of 3 different functions, so f, g, and h of x. Not as common, but it definitely works. So if you understand the product rule, the derivative of the first piece times the second, plus the derivative of the second piece times the first, this really follows the same general rule, and hopefully you'll start picking up on this. The first piece is going to be the derivative of f times g of x, h of x, plus, now I have to make sure that I include the derivative of g, so it's going to be the derivative of g of x. The other two, f and h, are just going to stay themselves. And then you probably already guessed it, now I have to do the derivative of h, and then I multiply that by f and g. So basically, each piece is going to have a separate derivative, and the other two functions are just going to stay themselves. So if you had 7 different functions being multiplied together, you would have seven different additions in there. And each piece would have one derivative, and all 6 other pieces would just be themselves. You'll never see one like that from me, but that's how it would work. All right. In our example, I kept the example relatively easy using polynomials so that we could get through it pretty quickly. This is something that you would probably FOIL out and distribute the x squared through and make it much easier just to do the power rule. But again, we're just going to show that this works for the product rule. So here, y prime would be the derivative. Now remember, you got 3 functions. 1, 2, 3 functions. The derivative of the first function, which is 2x, times the other 2. Plus the derivative now of the middle function, which is just 1, times the other 2. Plus the derivative of my last function, which is going to be 12x cubed times the other 2. So the biggest thing is just being careful, making sure that you incorporate all the pieces correctly. Obviously, we could simplify all this. We're not going to take the time to do that. If you would like to, take the time to simplify everything and then maybe double check against if you FOILed y out first and then took the power rule derivative, by all means go ahead and do so. It does work. All right, moving on to our next rule. Well, if there's a rule for products of functions, there's also a rule for quotients of functions, which just means division. So once again, f and g have to be differentiable. And the good thing here is, excuse me, if you understood or if you know the product rule derivative, this one is going to be very, very similar. So if you remember the product rule derivative, the way I wrote it was f prime g plus g prime x and g prime f. Well, it's going to be very similar. This is going to be f prime of x, g of x. And then over here, it's going to be g prime of x, f of x. So far, this looks exactly the same as our product rule. The only difference, pun intended, is that it's not plus now, it's minus because it's a quotient. Quotient is repeated subtraction where products are repeated addition. One other major difference here is because it is a quotient, it stays a quotient. So that whole thing is divided by the square of g of x. So there are different ways that people say this verbally in their head to kind of remember it. Instead of using first and second here, I use top and bottom. So the way I would say it is the derivative of the top times the bottom minus the derivative of the bottom, running out of room, times the top all over the bottom squared. So the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. All right, let's practice a couple. This will be a 2-video lesson, by the way. All right, so the first one, clearly a quotient, x plus 1 over x squared. We want to take the derivative. So according to our rules, it is the derivative of the top function, which is 1, times the bottom function, x squared, minus the derivative of the bottom function, 2x, times the top function, x plus 1, all over the bottom squared. Again, that is technically your derivative. Excuse me, sorry about that. I'm going to go ahead and clean this up just a little bit, distribute everything, simplify. You will eventually need to know how to do this, so it's probably good to practice it now. So on the top, you're going to get x squared minus 2x squared minus 2x over x to the 4th, which is going to simplify to negative x squared, because I got 1x squared minus 2x squared, so I get minus 1x squared minus 2x over x to the 4th. There is still an x in common in everything, so I can divide an x out, which is going to leave us with a negative x minus 2 over x cubed. And yes, you could certainly factor out a negative on top, but it's not necessary. That would probably be the simplest form that you'd want to leave it in. Okay, one thing about number 1, and we're going to see this later on in our second video, is this one technically did not need to be done using a quotient rule. We actually could have simplified this one using some basic algebra, divided each term by x squared, and done it that way. The second one, there's no way to simplify it. The first one, hopefully you can see, there is just one term in the denominator, x squared. So technically you can split all of your numerators on top of that common denominator. In number 2, I have 2 terms, x squared plus 1. That is the whole denominator and only one term on top. So I can't really split my numerator on top of 2 separate denominators. It doesn't work like that. So we have to do the quotient rule here. There's really no other choice. Well, that's not true. There is another choice, but it's not something that we're going to try and do with it for this particular problem. So the derivative of the top is 1 times the bottom, minus the derivative of the bottom, 2x, times the top, all over the denominator squared. We'll simplify it. So I've got x squared plus 1 minus 2x squared over x squared plus 1 squared. The numerator is going to give us a negative x squared plus 1. The denominator, there is really no need to FOIL that, so just leave it as x squared plus 1 squared. You're actually doing too much work, I think, if you end up FOILing it. Leaving it in that factored form is probably the easiest. And that's it. That's as far as that one's going to go. Okay, so we're going to do 2 more examples in this video, and then we're going to come back with a second video. All right, so in this case, number 3, once again, looks like it's pretty clear that we should do a quotient rule. So we'll go ahead and take the derivative of the top, which is 3, times the bottom, minus the derivative of the bottom, 8x, times the top, 3x minus 2, over the denominator squared, 4x squared plus 1, all squared. Okay, let's go ahead and simplify that. So 12x squared plus 3 minus 24x squared plus 16x, all over 4x squared plus 1 squared. Looks like the only other thing I can do here is to combine the x squared terms, so we get negative 12x squared plus 16x plus 3 all over 4x squared plus 1 squared. And that's it. That's your derivative. Again, technically, that first step there is the derivative. This is just simplified, and it's a good idea to practice the algebra now, even though the first answer is going to actually be acceptable. All right, if you look at the next one looks like it's much more difficult. It's really not, if you understand that you can rewrite this in multiple different ways. Probably the easiest thing, and the thing I think most people would probably see to do, is to change 11 over x to simply be 11x to the negative 1. So we're going to rewrite that numerator as 11x to the negative 1, and then over x squared plus 4. Now, the other way you could have simplified this, and if you saw to do it this way, this still works, you could multiply the numerator and the denominator by x and get rid of the compound fraction that way. Either way is perfectly fine. They're going to look a little bit different at the end until you actually fully simplify them, and we're not going to fully simplify both versions of this for purposes of this video. We're just going to take the derivative, but it can be done in multiple ways. So from our way, y prime is the derivative of the top, which is going to be 3 plus 11x to the negative 2. Remember, you're subtracting 1 from the exponent when you bring that negative 1 down. That's the derivative of the top times the bottom, minus the derivative of the bottom, which is 2x, times the top, all over the denominator squared. All right, we could simplify this one. I'm actually not going to waste the time in this particular case, but that's how you would do the derivative. So if you chose to multiply everything through by x, your derivative is going to look a little bit different. Again, until everything would be simplified down, they would both look the same. But that's it. That's how you're going to do the quotient rule. All right, so we're going to come back. We're going to do a few more examples of some derivatives where you don't necessarily need to use a quotient rule, even though it looks like you might. And then we're going to talk about higher order derivatives and some of their applications.